last time we met, I introduced topics in chapter 15 for solutions. And this is technically a buffer day, which is an overflow. So if we run short of time introducing the topic, then we'll have the opportunity to finish the topic on this day. But we finished the topic last Tuesday. So now we have the opportunity to use the buffer day for a little extra review. So I'm going to use the Cengage Homework as our to provide us with problems to work. It would be better if I had students here who could work the problems, and we could decide where the kinks were, where the problems in the problems are for my students, and then solve them. But I'm going to share the Cengage Homework location. If I can find it. I think it's here. There we go. All right. Last time I tried this, this shared screen did not record. So I'm hoping that it will work this time. If not, then I'll know not to try it again. But what we want to do, all of these items on the right are your homework problems. Right, so I'm not going to touch those. Those are for you to do. On the left are the problems that I did not select for your homework exercises. So these are extras. These are things that we can get extra practice on. And we're going to use these. So I'm going to start off with difficulty level 1 and do 2 or 3 of those. Then we'll work our way up through higher levels of difficulty. Okay, for this first one, we have, and as always, what I like to do when you have a word problem like this, read through it once, sort of get a feel for what's in there, what's the focus of the problem, and then look for the question. What is the question? The question is, calculate the mass percent of calcium chloride in the solution. All right. Let's see. Calculate the mass percent. All right. Then extract all the information from the problem and put it separate from the problem on a piece of paper, or I'm going to do it on the board. Then you get a chance to see what information is available to answer the question. You may not need all that information, or there may be some information missing that you have to go look up. For instance, molar masses in the periodic table is a common thing that is not given in the problem. All right, so what are we given? Now that we know the question, we're given 41.9 grams of calcium chloride. All right. And it's added to 174 grams of water. All right. If the question is the mass percent of calcium chloride, you need the formula for calculating mass percent. In this case, the calcium chloride is going to be in the numerator. Percent mass equals the mass of calcium chloride divided by the total mass. Correct? So we know the mass of calcium chloride. That's simple. 41.9 grams. What's the total mass? Well, the total mass includes calcium chloride too. That one plus this one. All right, times 100. Okay, I'm going to make a point here about significant figures. Notice that we have both rules operating here in this calculation. In other words, the add subtract rule and the multiply divide rule for significant figures. So which one comes first? Well, you have to do this one separate and then apply that one to the total. So if you add 41.9 to 174, nine, 5, 11, 2. So that would be the total, except we can only keep that part of the number. So this is rounded off to 216. Now, that's technically the correct way to approach this. You have 3 significant figures here, so you can still have 3 in the numerator, denominator, 3 in the numerator. So now with the divide rule, you have 3 in your answer. But I contend that applying this rule step by step, while it is correct, will probably introduce a rounding error. If we keep all of these together and do the calculation, then round to 3 significant figures at the end, what usually happens is you minimize the effect of rounding errors. So let's just do that calculation both ways. Right, let's use 216 divided into 41.9. All right, times 100. All right, so round it off to 3 significant figures. This one implies 19.4%. All right. Now, let's divide this one rather than that one. Right, save the rounding to the end. So 41.9 divided by 215.9 times 100 is 19.4. So there we have made a liar out of me. Well, actually, we got lucky. These numbers are so close together that the rounding error is insignificant. If this were 215.5, then we could possibly introduce a rounding error, and the number might be, instead of 19.4, it might be 19.5. All right. So let's enter that value here. We'll enter, well, they're both the same, so 19.4, and see if it gives us the correct answer, or we give it the correct answer. Okay, it likes the work. We did the calculation correctly, rounded off correctly. Now we're ready to go to another one. All right, let's see what the next one looks like here. This problem, and the thing about this Cengage Homework system is, if I go back to that original 15.022 here, the numbers will be changed. They vary. The problem will be the same, but the values will be slightly different. And that's by design. Okay. which means I can't develop a key for these problems because the values change. Let's read the problem, find the question. A solution is to be prepared that will be 1.76% by mass calcium chloride. To prepare 114 grams of the solution, what mass of calcium chloride will be needed? Okay, so this is along the same lines, but it approaches the problem from a different unknown value. Okay, so we're looking for what's the mass of calcium chloride. So if we've got 1.76% calcium chloride, and we want the total to be 114 grams. The question is, what's the mass of calcium chloride? Okay, now we have all of our information and the question separated from the problem. I mean, this is proper English, but it doesn't help you solve the problem. This is the way you solve the problem. Get the information up away from the syntax of grammar. Then you can see what you got and what you need. Okay, so the formula then is going to be percent is equal to the mass of calcium chloride, which is what we want, that's our unknown, and then the mass of calcium chloride plus the mass of the solvent, right? Now the solvent is probably water, right? But I just want to make the point that this is the solute. Whatever else is the solvent. Okay, how do we solve a problem like this? What do we know? We know this value right here, 1.76%. Times 100. Okay. We don't know this one, which is the same as this one. So what do you do in algebra? You set this one equal to some unknown, like make it x. So this would be x divided by x plus, well, actually, what is this value down here? That's x, yeah. What's this value? This value is 114, right? So we don't have to use the x down there. We can say x, total is 114 grams. We don't even have to put the unknown in the denominator because we know what the value is. We only need to solve for that x. Times 100. Okay, so put on your algebra hat and solve for that unknown. We would have, this is times on this side. That's kind of misleading, isn't it? There you go. Times 100. So this needs to be divided by 100, right? It's in the numerator here, denominator there. So x would actually be equal to 1.76 divided by 100 and then multiplied by 114, right? It's on the denominator here, it's in the numerator there, times 114. There you go. Now that's the thinking part, that's the hard part. This is just number crunching. So I get how many significant figures? 3. So that's 2.00. Okay. Now, how would you prove that to yourself? Well, plug the value in is one way. The other way is to use that value and calculate the percent. 2 grams divided by 114 times 100. 1.76%. Okay. All right. Let's do one more problem at the number 1 level. And see if the Cengage authors give us another approach, some other way to look at these types of problems. How many grams of KBr are contained in 177 grams of a 7.81% by mass KBr solution? Okay, so what do we know? Well, what's the question? Grams of KBr. So we want to know the mass of KBr. What do we know? We know the total mass is 177 grams. And we also know the percent, 7.81%. Right? That's equal to that unknown. Actually, this is the same type of problem as the one before, isn't it? So we need that one times this one divided by 100. And 3 significant figures is 13.8. So let's see if that works. There it is. Okay. Now I'm going to look at one more level 1 difficulty, just to see if they're going to start looking at different ways of expressing solution concentrations. Okay, here now we got some. So let's stay on level 1 for a little while, because now we're into molarity. I think we beat this horse to death, this percent by mass. So we can move on to something else. All right, a laboratory assistant needs to prepare 209 milliliters of 0.268 molar calcium chloride solution. How many grams of calcium chloride will she need? All right, so remember the formula for molarity. Moles per volume, right? And that volume must be in liters. All right, so what are we given? The total volume, which is this one, is equal to 209 milliliters. We're not given the moles of calcium chloride, are we? Actually, we're asked if we know the molarity is equal to 0.268 molar. The question is, what's the mass of calcium chloride that's needed? All right. So now, in order to find the moles, well, first of all, can we use that formula to directly calculate the mass of calcium chloride? No, we cannot. There's no mass in that formula. So we need to find out the moles of calcium chloride, then we can convert it to mass. So if we solve this for moles, right, molarity times volume. Can we use the volume as is? With this formula, we cannot use milliliters. We have to use liters. So how many liters is 209 milliliters? 1, 2, 3. 0.209 is the volume. And the molarity is 0.268. 0.268 molar times 0.209 liters. So that gives us the moles of calcium chloride. Which is 5.60 times 10 to the minus 2. All right, so now we need to convert that to mass. All right, so what do you need to do to find mass from that value? 5.60 times 10 to the minus 2 moles. Right, that's where we are. That's where we're headed, grams. So in order to do that, we need moles on the bottom, grams on the top. Whenever you see grams and moles in a quotient, you know molar mass. So how many grams of calcium chloride in 1 mole? We have to calculate it, right? We have, here it is, 1 calcium and 2 chlorines. So how much does a calcium weigh? 1 mole of calcium weighs 40.08 grams. And chlorine weighs 35.45 grams each. So that means 2 times that. Added together is 110.98. Do you need me? Okay. So now we're going to find out how many grams we have when we have that many moles. So I've already got this one in my calculator. I'm just going to multiply 5.6 times 10 to the minus 2. And I get 6.21 grams. Let's see if the system likes that answer. Indeed it does, within a certain amount of error, right? 6.22, 6.21. I built into these questions a certain percentage error for rounding problems, that type of thing. So it'll accept that answer. All right, let's see if we can find another molarity problem. Okay, here's another one. Let's see what it looks like. If 38.3 grams of sodium hydroxide is dissolved in water and diluted to a final volume of 111 milliliters, what's the molarity? All right, this is along the same lines, but in a different direction. So what do we have? We have 38.3 grams of sodium hydroxide. We also know that the final volume has to be 111 milliliters. Okay, the question is, what is the molarity? Okay, so based on the formula, we need the number of moles of sodium hydroxide divided by that volume, in liters. So how many liters is that? 0.111 liters. How many moles is that? We don't know yet. We need a conversion factor that will take grams and leave us with moles. So we need moles on top, grams on the bottom. Sodium hydroxide. Sodium is what? Well, you look at your periodic table. 23.00. 23.00. Oxygen is 16. Hydrogen is 1.01. So that's 40.01. That means we divide that into 38.3. So I get three significant figures, 0.957. 0.957 moles. Now we can put it into the formula. 0.957 moles divided by 0.111 liters. And I get 8.62 molar. So, right? Yeah, 62. There we go. Now let's see if the system likes that answer. Indeed it did. It's a little bit different. It's off, and the hundredths place is 1 unit different. Let's see here. Oh, Natasia's here. Okay. I got you covered. All right, so let's see. Let's see if there are any number one levels and if they're different in nature, right? Let's see. And let's skip that one. See if this one's any different. Here we go. Oh, a dilution problem. That's a good one. This one's multiple choice. So let's read the problem, look for the question. How would you prepare 160 milliliters of 0.194 molar sodium chloride solution if you're starting with 1.30 molar solution? So this is a dilution problem. So remember the formula. Molarity of concentrated, volume of concentrated equals molarity of dilute times volume of dilute. So what do we have given here? We got to put these in the right place, otherwise we can't get the right answer. How would you prepare 160 milliliters of? That's the final volume, the diluted volume, 160 milliliters. Okay, of a 0.194 molar sodium chloride solution. That's the diluted concentration, 0.194 molar. And you're beginning with a concentrated solution of 1.30 molar. Okay, so this way we can solve for volume. And remember, when you're using this formula, this ratio type formula, the volume doesn't have to be liters. It can be in milliliters. That just means that your answer is going to be in milliliters also. Okay, so let's find out what volume we need of the concentrated solution dissolved in a total volume of 160 milliliters, and see which one of these answers fits. So in order to solve for that one, you need this one times that one, divided by that one. So I get 23.8, 23.9. All right, let's see which one fits. Well, let's see. Final volume, 160 milliliters. All right. If we're going to prepare 160 milliliters, that's a given. It's got to be these first three. It can't be the last one. So let's see. 71.6 milliliters of 1.9 is too much. We only need 23.9. It looks like this one. Dilute 23.9 milliliters of the 1.3 molar solution to a final volume of 160. That looks like what we would be doing. You dilute the concentrated to that volume, and it gives you this concentration. There. I think it likes it. All right. That was fairly simple. I like simple. Even when the problem is complex, I still like simple. In other words, I take a complex problem and I bust it apart into pieces that are simple, and then bring them back together to answer the question. All right. So let's see if there are any more difficulty ones of a different bent, so we can get some practice doing these type of problems. Okay, this looks different. Many metal ions are precipitated from a solution by the sulfide ion. As an example, consider treating a solution of copper 2 sulfate, and they give you the equation. Copper 2 sulfate, and you treat it with sodium sulfide. So we look at those and say, all right, is that correct? Copper 2 sulfate. If that's the formula, this is the 2 minus charge on a polyatomic, so this one has to be 2 plus. That one's correct. In aqueous solution. How about sodium sulfide? Is that one correct? Sulfur is a chalcogen. It's in the oxygen group, so it has a 2 minus charge. Sodium has a 1 plus charge because it's an alkali metal. So we need 2 of them. That's correct. Okay. What else do we have? Copper 2 sulfate. No, copper 2 sulfide is one of the products. And it's insoluble. So it precipitates out of solution. And then you have the what's left over in solution. Okay, let's see if that equation is balanced. There's 1 copper, 1 copper, sulfate, sulfate, 2 sodium, 2 sodiums, 1 sulfide, 1 sulfide. We're balanced. And now we can proceed. What volume of 0.18 molar sodium sulfide solution would be required to precipitate all of the copper ions from a 29.1 milliliter of 0.121 molar copper sulfate solution. All right, so let's put what we know up here against our balanced equation. What volume of 0.108 molar, 0.108 molar solution, and we have 29.1 milliliters of this, times it's 0.121 molar, 0.121 molar. So what volume in milliliters? Here, volume, that's the question. How much of this, what volume of that is required to precipitate all of this? Okay. Remember, when you're going to use stoichiometry, you have to go to moles. You got to find moles. So how many moles of this do we have? Well, there are two possibilities. We can say molarity times volume equals moles. That's true. So molarity times volume in liters would give us actual moles. But I'm going to show you a trick. If you multiply milliliters times molarity, you get millimoles. So molarity can be expressed as moles per liter. But if you multiply both of these by the same number, you haven't changed anything, right? That's algebra. That's mathematics. If I multiply this one times, say, times 2, multiply this one times 2, the ratio is still the same. So what if I multiply this one times 10 to the minus 3? And this one times 10 to the minus 3, right? 10 to the minus 3 divided by 10 minus 3 is 1, right? So you're multiplying that by 1, which is permissible. So what is this equal to? 10 to the minus 3 liters is a milliliter. And 10 to the minus 3 moles is a millimole. There you go. So now, if we rearrange and say volume in milliliters times molarity, and this is in milliliters, then your answer is going to be moles in millimoles. Right. So this way, you can avoid having to do conversions to liters. It just saves you a couple of steps. You have one step on this side and one step on that side to give you moles here and to give you milliliters there. So this way, you just circumvent that whole problem once you realize that this is true. So if we multiply that times that, we get millimoles of copper sulfate. So let's do that. Times 29.1 milliliters and 0.121 molarity is 3.521 millimoles. 3.521 millimoles. Now, if you need moles, right, all you have to do is convert that. Multiply that times 10 to the minus 3 and you get moles. But we don't need to do that because we're going to say this is millimoles of copper sulfate. Right? Convert that to millimoles of sodium sulfate, copper sulfate, sodium sulfate, right? And the ratio is 1 to 1. So that means we need, right, cancel, cancel. We need 3.521 millimoles of sodium sulfate. All right, remember the relationship. This times volume equals that. 0.108 molar times volume in milliliters equals 3.5121 millimoles. Okay? So this is just that number divided by this number. .6 milliliters. Okay, so there you have it. 32.6. Okay, and as luck would have it, the explanation given by the Cengage virtual machine here introduces that concept of millimoles. So I just proved to you that it works. They just went ahead and used it. But I showed you that why it works. So that was a little stoichiometry using solution concentrations and volumes. All right, let's see. I can't see myself. There I am. Just checking. There we go. Okay, that was fun. Let's see if we got another one that can be. There's a number one. Okay, this is a titration. But it's similar to the last one, only now we've got acid-base reaction. So let's just work this one and see if there are any kinks in this armor. All right, the question is, what volume of sodium hydroxide do you need? Volume of sodium hydroxide. Right. Well, let's write the reaction first, right? We know that we're going to add sodium hydroxide solution to nitric acid solution. Okay, what is that going to give you? Every acid-base reaction gives you two things. A salt, using the cation from one and the anion from the other. In this case, it's soluble, plus water, and that's a liquid. Okay? Now let's see, is that balanced? There's one hydrogen. There's another hydrogen. Two hydrogens. There's an oxygen. There's an oxygen. There's a nitrate. There's a nitrate. There's a sodium, sodium. That equation is balanced. Now we can insert the information we have. All right, so we have 0.694 molar sodium hydroxide, 0.694 molar. We also have 0.377 molar HNO3, 0.377 molar. But we have a definite volume of this one, 24.9 milliliters, 24.9 milliliters. What we want to know is what volume of this one is required to exactly, what's the stoichiometric equivalence of this one to that one. So this volume is our unknown. In milliliters, right? Yes, the answer should be in milliliters. So we can use our millimolar relationship, right? In order for these two to be equal, you need the same number of moles of this one as that one, right? So how many millimoles of this one do you have? Well, there's only one proton here. There's only one hydroxyl here. So we can say this molar concentration is also the hydroxyl concentration. It's 1-to-1. And this concentration is the proton concentration, right? So molarity times volume here has to equal molarity times volume there, right? That's the number of moles. Number of moles of hydrogens equals the number of moles of hydroxyl, right? So how do you get the number of moles of this one? 0.377 molar times 24.9 milliliters. And this one you have 0.694 molar times volume. There you go. Moles equals moles. Moles of this equals moles of that. Or millimoles equals millimoles. Same difference. So we need this one times that one, 0.377, 24.9, and then divide by this one, 694. I'm using the right, I'm using the right numbers. So I get 13.5 milliliters. Does that look reasonable? This one is a more concentrated solution. It's about double that one. So this one should take half the volume to give you the number of moles you need of that one. So about half of that is 12 and a half, 13 and a half. All right, we're in the ballpark. So that's estimation to see if we're close. 13 and a half. Now to find out if it's exactly the right answer, you put that value in. And turns out it is. It is equal. Now, what would you do if this one were sulfuric acid? Right now it has a different ratio. It has 2 protons here. So the molarity of the protons in sulfuric would be twice that. If this is the molarity of the H2SO4, then the molarity of the protons would be twice that. And that's what we were discussing at the end of the last introduction 2 days ago. Normality. That's where normality comes in. When you use normality, then it doesn't matter what these are. This relationship, normality times volume equals normality times volume. And it doesn't matter where the normality comes from. That's the advantage of using that unit of measure. All right, let's see if we've got any more number 1 difficulties here. Speak of the devil. There's a problem with sulfuric acid in it. All right. Only when we're talking about normality, we've decided to use a different unit. Rather than moles, we call it equivalents. So let's see if we can work this problem. Well, actually, look here. They're using not molarity, but they're using normality. They've already done the calculation for us, right? So when we add sulfuric acid together with sodium hydroxide to yield sodium sulfate plus water. To balance that equation, we need two of these. And that's it. We're balanced. But if we're using normality, we don't need to use the stoichiometry of the equation because normality incorporates acid-base stoichiometry in itself. Why? Because the net equation is hydrogen ions plus hydroxyl ions yield water. So if we know the concentration of this relative to that, we can set up our equivalents. So we have the normality of the acid times the volume of the acid equals the normality of the base times the volume of the base. Okay, that's the advantage of using normality. Now we know what the values are. 0.52 normal sodium hydroxide. So 0.52 normal sodium hydroxide and 0.34 normal sulfuric acid. 0.34 normal. And we have a volume there, 14.5 milliliters. And the same reasoning behind milli-equivalents, millimoles, works for milli-equivalents. So this times that gives you milli-equivalents. So this is your acid, and you would have 0.34 normal times 14.5 milliliters equals the normality of the base, 0.52 normal times the volume of the base. And that should give us the answer. So we need this times this, divided by that. And we only have two significant figures, so it's 9.5 milliliters. Volume of the base, 9.5 milliliters. All right, let's see if the system likes that answer. In fact, it does. Okay? So that's the advantage. For acid-base reactions, normality is very useful. This formula holds for normality. It does not hold for molarity. Because molarity, unless you do that preliminary calculation for molarity of acid or protons, and normality already does that for you. All right, so let's see if we got a number one down here. There's one. See if this is different. What mass of KNO3 is required to prepare 136 grams of 1.8%? All right, we've done one like that before. We're not going to do that one again. I mean, it's good to work multiple problems like that when you have the time, but we're limited on time. And we're still in difficulty 1. We need to get moving. Nah, that's nothing new. This may be all level 1 problems that Yeah, that's a dilution problem. How about this level 1? Nah, let's move on. Okay, that's all level 1s. Let's go back to the top and look at difficulty 2, molarity of a solution. All right, let's see. My board's walking a little bit. Let me bring it back. There we go. Well, okay, let's do this one. Simply because it's a word problem and the compound is named, but the formula is not given. Right? In order to solve this problem, you have to know the formula. Right? So let's work this one. All right, what's the molarity of this solution? So that's our question. What's the molarity? What are we given? 32.8 grams of sodium carbonate. 32.80. Yep. Sodium carbonate. All right, we know we have sodium in it. Carbonate is a polyatomic ion. So you have to look that one up in that table, the polyatomic table, if you don't already know it. Okay, what's the charge? Sodium's always +1. It's an alkali metal. Carbonate is always 2-. Polyatomics have fixed charges. They don't change. Okay? So now to balance that, we need 2 of these. Right? 2 pluses balance a 2-. All right. So now that we know that, we have the formula. And the final volume is 1150 milliliters. 0.0 milliliters equals total volume. Okay, to satisfy the formula, this needs to be in liters, right? This is not one of those ratios. This is the definition of molarity. This has to be in liters, which is what? 1, 2, 3. 1.1500 liters equals volume. What else do we need? We need moles. Moles of that compound. All right, so you're going to have to look it up and calculate the molar mass of that compound. So we got 2 sodiums, right? We look at our periodic table. 23.00. For sodium, carbon is 12.01. Oxygen, 16 times 3, which is, I think, 48. Yeah, and add that in. So I get 83.01. Let me be sure I did that right. Let me do it again. 23, enter 2 times. Then add carbon. And then add 48. See, I did my calculation wrong. It's a good thing I checked it. It's 106.01. Okay, so we need to convert this many grams cancel the grams, leaves us with moles. Right? 106.01. So we divide that into 32.80. And I get 0.3094. 0.3094 moles. Okay, now we can calculate molarity. 0.3094 divided by 1.1500 liters. There we go. So I got 0.2690. 0.2690 molar. Now let's see, can I keep all of those decimals? This is 4, right? So I got 4 over here. This is 5, so I got 5 there, so I can keep 4, right? 0.2690 should be the accepted answer. Oh, it's not going to explain it, just says it's correct. Okay. We'll take it. All right. That was level difficulty 2. Let's scroll down and see if we can find another 2. How about this one? Concentration of a base. Okay. Put on our thinking cap here. We're reacting calcium hydroxide solution with a nitric acid solution. And the goal is to calculate the exact concentration of the calcium hydroxide. All right, so we've got a titration going on here, and we need stoichiometry to answer the question. So we need a balanced equation, the reaction of that base with the acid. And so we have calcium hydroxide, aqueous, right? And we have nitric acid. They don't tell you what nitric acid is. They just name it. So you have to be able to write nitric acid. Remember, there's oxygen in this molecule because we don't say hydro. So nitric, remember, X come from 8s. So nitrate is the origin of that acid. That's a -1 charge, so we only have 1 hydrogen to balance it. So what do we get out of that? Well, we get calcium and nitrate. Calcium. This is a 2+, that's a 1-. So we need 2 of those. Remember, all nitrates are soluble, plus water. All right. So now we need to balance the equation. There's a calcium, there's a calcium. There's a hydrogen, and there's a nitrate. We need 2 nitrates. Let's do that. There we go. Now we have 2 hydrogens and 2 hydroxyls, which makes 2 waters. Now we're balanced. Okay, let's add the information that we know. A 50 milliliter sample of aqueous calcium hydroxide. 50. So 2 zeros? Yep. And when we titrate it to the endpoint, that is, when we know that they're equivalent, stoichiometry is exact, then we have used 34.66 milliliters of this standard solution of 0.822 molar. Okay, so the question is, what's the molarity of this one? Well, we could go 2 routes here. We could either do normality, but the question is asking for molarity, right? So we're going to use stoichiometry. That means how many millimoles of this are required. How many millimoles of acid are required? That one times that one. 0.822 times that. So I get 28.49 millimoles. 28.49 millimoles of nitric acid. So what's the ratio? If this is nitric acid, what's the stoichiometry say? Okay. 2 of these for every one of those, right? 2 to 1. So how many millimoles of calcium hydroxide do we have? 28.49 divided by 2. So that's 14.25. 14.25 millimoles of calcium hydroxide. Okay, so to calculate the concentration, we just need millimoles per milliliter. Remember, if they're both milli, then the answer is in molars. So if we say millimoles per milliliter, we get an answer in molarity, just like I showed you earlier. So divide that by 50. And let's see, we have 4 significant figures. So it's 0.2849. All right, let's see if the system likes that answer. It certainly does. Okay. Now, if you were taking general chemistry, we would have a lab, and the lab experience would give you, you do one of these types of problems in the lab, hands-on. Well, if we were face-to-face, you would. That's a separate issue. But we use this type of titration over and over again in the laboratory setting. It's a process called standardization. So if you know that the exact concentration of your acid is this here, then you can use that knowledge and titrate a base of an unknown concentration and standardize the base. Bases are notoriously unstable. We use sodium hydroxide standardized base a lot in the lab, but it doesn't keep for very long. So periodically you have to re-standardize it with an acid that is very stable. Sodium hydroxide exposed to the atmosphere absorbs carbon dioxide from the atmosphere, and it yields sodium carbonate. Right? That's not balanced, but that's the gist of the idea. This is not the same as that. So if you standardize for this one and you wait 6 months and use it again, some of it might be like that. Now, there are ways to preserve sodium hydroxide in a container, especially if you're going to use a lot of it. You standardize a huge tank of sodium hydroxide solution, then you can use it for months and months and months if you protect it. Right? So what you do is you have a bottle. Here. It's got a stopper in it. And then there's a tube that goes down here like this. And that delivers your sodium hydroxide. You just pump it out. So what happens to the airspace up here? Well, it wants to pull atmosphere in there, right, with carbon dioxide. So what do? Well, you put yourself a bulb here that allows air to come in. But inside that bulb, you have some sodium hydroxide or some other base that probably wouldn't use sodium hydroxide. It absorbs too much water. But you would have something in there that would absorb the carbon dioxide as it tried to get into the bottle, and then you preserve the concentration of your sodium hydroxide that way. There are other types of carbon dioxide absorbents. Right off the top of my head, I can't remember what they are. I haven't used it in so many years. Now, when the astronauts go into space, they take with them a filtering system, right? Because as you breathe in oxygen, you breathe out carbon dioxide. So if the carbon dioxide builds up too high, you start to get loopy. So they filter the air through usually lithium hydroxide because it's much, much lighter than sodium hydroxide. And weight means everything in space. You got to get it up there, right? So each pound costs thousands of dollars. So they use lithium hydroxide and they filter the air through that, and it absorbs the carbon dioxide, and then you can just keep working. All right, so let's see. Neutralization, do we want to tackle this one? Nah, let's look at solubility in a solvent. Did we talk about polar and non-polar solvents? I think we did. Yeah, I think we did. So let's look at this one, right? Let's decide whether each one of these is soluble. What's the best solvent for octane? Octane is basically gasoline, right? You put in the tank of your car and burn it. There are some additives in there, but it's predominantly octane. Octane is a long chain, long carbon chain, lots of hydrogens on it. It is non-polar. So the best solvent for this one would be the non-polar solvent, which is carbon tetrachloride. How about sodium hydroxide? Sodium hydroxide is an ionic compound. It breaks apart into sodium and hydroxide ions. So it needs a polar solvent. Water. How about ammonia? Ammonia, I think, is polar, right? I think I drew this one for you. Right? It's polar in that direction. So I would think water would be the best solvent for this one. How about cesium carbon disulfide? Okay, this one's a little trickier. I could just tell you that carbon disulfide is nonpolar. The reason being, it's like that. And I think It's got lone pairs out here like this. Those are electrons, 2, 4, 2, 4. But it's a linear molecule. So even though the polarity is this way and that way, they're equal. They cancel each other out. So carbon disulfide is a nonpolar solute, so it needs a nonpolar solvent. How about this one? That's a long chain fatty acid, right? You can tell because of this group right here. And it occurs in your food and in your body. I can't remember which one this is. It's got 12 carbons. Palmitic acid, maybe? I'm not sure. Anyway, it is polar because of this end right here. So it would dissolve. Actually, it could dissolve well in either one. But I'm looking at this polar end here and think that maybe water is the best one. So let's see if that our choices are acceptable. Partially correct. Okay. So it's saying that this one is nonpolar. So that acid group out here is not quite polar enough to dissolve in a polar solvent. So it's saying that that one needs to be a nonpolar solvent. Let's see. What is it going to say? Try another version. Well, let's see. Here's that's a methyl cyanide, and I'm thinking cyanide is a polar part of the molecule. There's another one. Okay, so we're going to say this one's nonpolar, and we're going to say this one. This is the long chain alcohol. I don't know what it's going to say for that one. Could be water, could be carbon tetrachloride. Let's just say carbon tetrachloride. This one's definitely nonpolar. And this one, C2H3O2, you should recognize that as acetic acid. That's water. Now let's see what it thinks. Okay, it liked my answers. I think the key here is that when you have these long chains here out to the end, it adds nonpolar characteristic to it that overwhelms the polar nature of that one end unit out there. Okay, so let's see what more trouble we can get into here. There's a 2. How are we doing on time? 10:30? We're good. I think we're good till what? 11:50? Yeah, 11:50. So we got time to work through some number 3s and 4s and maybe even come back to a 5. Solubility, we did that one already. How about this number 2? What is that one? Calculate the mass in grams of solute present in each of the following solutions. All right, we've done one like that before. I'm not going to spend time on that one. That's another one. Let's see if we can find something here that's has multiple answers to it. What mass? All right, we've done problems like this before. Finding the mass of a known amount of a molar solution. Okay, maybe what we need to do is graduate to a level 3. This one might be interesting. Might even be a challenge for me. I have to figure out what are they actually asking here. aluminum ions can be precipitated from aqueous solution by adding hydroxide. Aluminum hydroxide has very limited solubility. But if you add an excess of hydroxide ions, you can cause the aluminum to go back into solution. All right. So the question is, how many grams of sodium hydroxide should be added to 10.8 milliliters of 0.104 molar aluminum chloride to just precipitate all the aluminum? All right. What I'm thinking is, you don't want any excess hydroxide. That's what this statement says. So if you want to just precipitate all the aluminum, that's a stoichiometry problem. You want just enough hydroxides to be just enough to make aluminum hydroxide and no extra hydroxides. So here's what we would do. We want aluminum ions are precipitated from aqueous solution. So we have aluminum ions, and it really doesn't matter what the source is. And then we're adding sodium hydroxide. All right. And what does that yield? Well, it yields sodium ions plus aluminum, excuse me. I have the feeling we're going to need some space in here. Plus aluminum hydroxide. Right? And this is going to be a solid only if we're stoichiometric. So let's balance the equation, right? It seems odd to me we've got ions in here. Believe me, you can balance it. Aluminum here, aluminum there, 1 to 1. Sodium here, sodium there. Hydroxide. Okay, we need 3 hydroxides. Right? But now that gives us 3 sodiums. So now we're balanced. Okay. So that's the balanced equation that we're working from. So how many grams of solid sodium hydroxide? So we're looking for the mass here. 10.8 milliliters. Let's see. Oh, it is telling us aluminum chloride. All right. So this is, excuse me, we can put a compound here. Aluminum chloride and sodium chloride. It doesn't change anything. Right? We got 3 chlorides, 3 chlorides, 3 sodiums, 3 sodiums, 1 aluminum, 1 aluminum, 3 hydroxides, 3 hydroxides. Didn't change a thing. But if we need to do any mass conversions, we need to know that compound. Okay. 10.8 milliliters of a 0.104 molar solution. Okay. So I'm thinking we just find out how many millimoles is that. .104 times 10.8. 1.123. 1.123 millimoles. Okay. How many millimoles of sodium hydroxide is that? Well, the ratio is 1 here and 3 there. Okay. So 3 times this is equal to how many millimoles of sodium hydroxide? 3.369. 3.370 rounded off. 3.370 millimoles. Okay. So if we're going to be in grams, this has to be in moles. Right? So here's the way I do it. Take this milli and put it out here. Milli means 10 to the minus 3, doesn't it? So now this is out there, and it's 3.370 times 10 to the minus 3rd moles. Now, we just need the molar mass of sodium hydroxide. Okay? Sodium's 23, I believe. Yep, 23. Oxygen 16. Hydrogen is 1.01. 40.01. There we go. Now we multiply 40.01 times 3.37 times 10 to the minus 3. I get 0.13, 3 significant figures, 0.135. Grams of solid sodium hydroxide. Okay, it worked. And it looks like they used the exact same steps, except for their value for the molar mass of sodium hydroxide was 40.00. So they rounded error to something. They probably rounded hydrogen. They said hydrogen is 1, but it's actually 1.01. All right. So that was, let's see. Let's scroll down and see if we can find any more 2s that are interesting. We've done that one before. Neutralization reactions. This should go pretty quick. Calculate the normality of each of these solutions. All right. One thing that simplifies the whole process, if the acid only has 1 proton per molecule, the molarity equals the normality. There's no conversion required. So this one would be 0.724. Okay? Sulfuric acid, we have to think in terms of equivalence. When you have this many moles per liter, right, 1.37, actually, how many moles per liter, how many equivalents per liter do you have? Right? You have 2. You have 2 equivalents for every 1 mole. So that would be 0.1, oh, excuse me, 1 second. Yes, I had to think for just a second to be sure I'm correct. Yeah, you have 2 equivalents of hydrogens for every 1 mole of H2SO4. So 0.137 times 2 is 0.274. Okay, So what do? If you know the molarity of your acid, then you calculate how many hydrogens are there, how many acidic hydrogens are there. In this case, 2. In the next case, there are actually 3. So 3.5 times 10 to the minus 2 times 3 hydrogens is 0.105. Okay? Now, what if these were bases? I wonder if maybe they've got a base problem up here. No. We could do this one. But if you have a base, you just look for the number of hydroxyls. Right? So if you have 1 hydroxyl, then the molarity and the normality are exactly equal. If you have 2 hydroxyls, like calcium hydroxide, then molarity times 2 gives you the normality. If you have 3, like aluminum hydroxide, and that would have to, right, we learned that it's insoluble unless you get a lot of it in solution, so that's a bad choice. Let's pick a different one. How about I can't think of a good one. Not equivalent to 3 hydrogens, 3 hydroxyls. Okay, so let's look at this one. A solution of phosphoric acid, H3PO4, is found to contain 21.1 grams of H3PO4 per liter. Calculate the molarity and the normality. Right? This one should be fairly simple. Right? 21.10 grams. Of H3PO4. How many moles is that? Right? We need the molar mass of H3PO4. 3 hydrogens, 3.03. Phosphorus, I have to look that one up. Phosphorus is 30.97. 30.97. And 4 oxygens is 16, 32, 64. 98.00. So we divide this into that. And I get 0.2153. 0.2153 moles. Okay? And per liter, right? So that's already per liter. So that's equal to 0.2153 molar. So what's the normality? 3 times that, because you have 3 hydrogens. .6460. 0.6460. Normal. Okay, so let's plug those numbers in and see if the system likes it. 0.2153. Broke my own rule. Preceded with a 0. And 0.6460. There you go. See, they used a different value for the molar mass. Oh well. One thing you'll notice is if you look on the bottle of a chemical, it will give you the, sometimes it's listed as FW. That means formula weight. How many grams per mole is that formula? And what the chemical bottle does is it takes into account impurities, right? It's not 100% of that chemical. So the formula weight in that bottle depends on its purity. Whereas if you calculate it from the periodic table, you're assuming 100% purity, and my value said 98. Their value said 97.99. They were probably reading it off the bottle, which is okay. I mean, that's, in fact, it's probably more, it's accurate that way. All right, let's see, let's move this back over here. There we go. Let's see. There's a 2, we have another 2. Let's try this 2, see what it looks like. How many moles and how many grams of indicated solute does the following solution? All right. That's no challenge there. Okay. No more 2s. So let me scroll up just a little bit so we can see more of it. Let's go back up to the top and look for 3s. All right. And see, there's a 3. More and more difficult. All right, let's see what this one says. You have 341 milliliters of a 1.25 molar potassium chloride solution. But you need to make a 0.5 molar potassium chloride solution. How many milliliters of water must you add to the original 1.25 molar solution to make the 0.5 molar potassium chloride solution? And you also have to make the assumption when you add that extra solvent, that volume adds to the total. For dilute solutions, that works. For concentrated solutions, it might not be exactly that. You may add 100 milliliters, but it only brings the total volume up 99 milliliters. For valid chemical reasons that we won't discuss here. But to work this problem, we're going to say, assume the volumes are additive. That is, if you add 100 milliliters, that increases the total volume by 100 milliliters. Okay, let's put the numbers, extract them from here, and then go back to the question. 341 milliliters of 1.25 molar potassium chloride. 341 milliliters of 1.25 molar potassium chloride. Okay. But you need to make a 0.5. So this is the concentrated volume. This is the concentrated molarity. You need a diluted molarity of 0.5. And what we don't know here is or do we know the diluted volume? What is the diluted volume? How many milliliters of water must be added? Okay, so we don't know the diluted volume, but the diluted volume is how much do you want to add? X milliliters plus 341 milliliters. See what that means? This is what we have to add to that total volume. We're going to dilute the entire thing and get this concentration. So how much water do we need to add to dilute it down to this concentration? So that's the twist in this problem, is it's not the total volume that you're looking for, it's that value. So now we can set everything into the formula. So I'm going to go right in here. So the concentrated volume times the concentrated molarity. 1.25 molar times 341 milliliters equals 0.5 molar times X plus 341 milliliters. Now we have an algebraic equation that we can solve for one unknown. So how do we do that? Well, that's multiplied by that, so we take this and divide it into this product. 1.25 times 341 divided by that one equals 852.5. 852.5, which is what? Milliliters, right? Molarity cancels, leaves us with milliliters, equals X plus 341 milliliters. So X is the difference between this one and that one. So we just subtract 341 from this value, and we get rounded off 512. X equals 512 milliliters. Okay. Let's see if it likes that answer. It certainly does. Apparently these chem work problems don't give you any explanation at the end. They just say right or wrong. Okay. Every time I wipe the board, I make it walk a little bit. So I'm going to reposition. There we go. Okay. So let's see. That was a level 3 difficulty. Here's another one. See if this one gives us a challenge. To make 1.5 liters of 0.1 molar sodium chloride from a 2.92 molar stock solution, you would need to take so many milliliters of stock and add so many milliliters of water. That's nothing new. We can do that in our sleep, can't we? Or do we need to do that one? Yeah, let's do it. We got time. So, what are we given? We need to make 1.5 liters of a 0.1 molar sodium chloride solution. So, if we got molarity concentrated times volume concentrated equals molarity diluted times volume diluted, where do these numbers go? We're going to make 1.5 liters. That's the diluted volume. 1.5 liters. And the concentration needs to be 0.1 molar. 0.1 molar. Okay. What else? We're making this from a 2.92 molar stock solution. So the question is, how much of that solution needs to be diluted and how much water do you add? Haha. Okay, so we do need to find out what this is right here. So we might as well solve for that one. So that says how much volume of the stock concentrated solution do we need? And then how much water do we need to add to make 1.5 liters? Okay, so this one times that one, which is 0.15, 0.15, divided by this one is 0.05137 liters. Okay? How many milliliters is that? All right. The units are getting smaller. They're going from liters to milliliters, getting smaller. So the number has to get bigger. So we move to the right. 1, 2, 3. Volume then equals 51.37 milliliters. So that's how much of the stock solution we need. I'll go ahead and put that one in. 51.37. And how much water do we need to add in milliliters? Right. So how many milliliters is 1.5 liters? 3 positions. 1,500 milliliters. Minus 51.37 equals how much water that we need to add. Because this is the total. Subtract the volume of the concentrated solution, and then how much water are you adding? Let's see. Do this conversion. There we go. And then 1,500. So I get 1449. Let's see if it likes my decimals. It liked it. Okay. Just when you think these problems can't get any more complicated, they do. All right, that was a 3. See if there are any more 3s down here worth looking at. Yeah, okay. 450 milliliter sample of 0.296 molar silver nitrate is mixed with 400 milliliters of 0.2 molar calcium chloride. What's the concentration of chloride in solution after the reaction is complete? All right, we're going to need a balanced equation for this one. Silver nitrate. I'm going to move over here a little bit. Silver nitrate. Silver is +1, nitrate is -1. That's the way you write it. Plus calcium chloride. Calcium chloride. Need 2 of those because chlorine is, the chloride ion is -1, calcium is +2. So we need 2 negatives to balance that one. That's aqueous. So what do you get from that solution? Right? It doesn't tell you what you get, because this is one of those situations where you automatically know these are all ions in solution, correct? Silver ion, nitrate ion, calcium ion, chloride ions. You just swap the cations. Swap this one for that one, and you get silver chloride, which precipitates, right? Look it up in your table of solubilities. Before I say that, have I given you one of those? I haven't looked. Let me look. Just take a second and look to be sure. Sorry. Move. Yeah. Here we go. This is the review document for Chapter 15 that you can find in Blackboard. And at the back of this document, you know, we need to talk about this. We've done polyatomic ions. There's your polyatomic ion table, right? You've seen that before. But we didn't talk about solubility. All right? So here's your solubility table right there. All right, I'm going to have to show you how to use that. And let's work this problem, and then I'll stop this share and pull that up and show you how to use that thing. You know, on second thought, you know, if I stop the share and try to come back to it, it should still be there. Yeah. So let me stop this share. Stop that share. Okay. How do you interpret this table? Notice when you have these aqueous solutions, what you actually have in this case is silver plus nitrate plus calcium. In fact, this thing is not balanced yet. Let's balance it. We need two of these, one calcium. I didn't finish this out here. Calcium nitrate. Right. So there's two silvers, two nitrates, one calcium, two chlorides. Okay, now it's balanced. So now you have two silvers, two nitrates, one calcium, and two chlorides. All right, on the reactive side. So what happens is everything's in the same solution. It's all mixed together. So this calcium is looking at that nitrate, right? It comes from the chloride, but you know, maybe it doesn't like that relationship. So it goes over here and says, all right, maybe nitrate's better. So we look at calcium, which is up here along the top. The cations are up here at the top, right here, right there. And then nitrate is down the left-hand side here, nitrate. So you look calcium, nitrate, where they cross, right there in that block is clear, which means calcium nitrate is soluble. So that is aqueous solution. Okay. Now, silver looks at chloride. Silver looks at chloride and says, all right, what kind of relationship can I have with this one? So you look for silver up here, right? You go across, there's silver right there. And then you go down until you intersect with chloride row. Here's chloride. So chloride goes over here, silver's there, it's gray. That means silver chloride is insoluble, forms a solid in solution. So that's why I wrote this one right here. Okay, that's how you interpret this thing, this chart, rather than having to learn all the rules. Because you'll notice that the rules are down here at the bottom, right? And if you were, well, actually, I don't even make my general chemistry students memorize it. Just use the chart. There we go. Right, and that chart is in the next to the last page of your review document. Actually, third to the last page of your review document. Okay, so now that we know which one is solid, in other words, it precipitates out of solution. We've put these two solutions together, which you can see through, and you can shine a light through, and then put them together, and you get this solid, and you shine the light, and you can see the light beam. That means you've got to precipitate right there. Okay, so let me stop the share and we'll go back to the problem and hopefully it'll still be there. So let's share again. Let's go back to Cengage right here. It looks like, well, actually it doesn't matter because we haven't worked the problem yet. So even if it did change, it wouldn't matter. Okay, now we've got the balanced equation, and I'm going to erase this part here. Now that the explanation is done. Okay, so what are we given? We're given 450 milliliters of 0.296 silver nitrate. 450.0 milliliters of 0.296 molar silver nitrate. And you add that together with 400 milliliters of 0.2 molar calcium chloride. There we go. Now remember, once you've got your balanced equation, we've written the compounds correctly, we've balanced the equation, we put what we know in here. First thing to recognize is if you're given an exact amount of reactants, one of them is going to run out. So you need to find the limiting reactant and consequently the excess. All right. So if the question is, what's the concentration of chloride ion in solution after the reaction, then this chloride is tied up in the solid. So we need to know how much of that chloride is there. And then subtract it to how much we started with. And that gives us the number of moles of chloride left over. And based on the language of the problem, this is probably excess, but we don't know that yet. So we got to find out which one is limiting, which one's excess. Because if this one's limiting, then there's no chloride left over. So let's do that first. All right. So, how many millimoles of this do we have? And how many millimoles of this do we have? That's our first calculation. 450 times 0.296 is 133.2 millimoles. Okay. This one is 400 times 0.2, which should be 80. Is that right? A tenth of that would be 40 and 2/10 would be 80. Yeah, that's right. Okay, now which one runs out? Well, we can look at it in terms of how much of this is produced. That's the way I like to do it. So 133.2, 2 to 2 or 1 to 1. So this would produce exactly that many millimoles of silver chloride. This one is 1 to 2. So for every one of these, you get 2 of those. Right? So this would be 2 times that. 160 millimoles. All right? So which one is limiting? As we suspected, silver nitrate is limiting, right? 133 versus 160. Right? So this is the actual amount of silver chloride that is produced. How many millimoles of chloride ions are required for that solid? 130. See, it's 1 to 1. One of these, one of these. So this implies 133.2 millimoles of chloride consumed. All right. So how many millimoles of chloride do you start with? Well, we go back to this one. That's 80 millimoles of calcium chloride. How many millimoles of chloride do you start with? 2 chlorides for every 1 of these. So you actually start off with 160 millimoles of chloride ions. So what's left over? Well, this is sequestered in that solid. So you subtract 133.2 to find out how many millimoles of chloride are left over. .8 millimoles of chloride in solution. All right, we're almost there. Now we know how many millimoles of chloride there are. How many milliliters of total solution are there? Because if we divide millimoles by milliliters, total solution, we've got our molarity. And that's the answer that's looked for right here. So what's the total? 450 plus 400. So the total is 850 milliliters. So we divide 850 into 26.8, and we get 0.315. 0.315. 0.0315. There you go. So let's put that in and see if the system likes it. 0.0315. It enjoyed that one immensely. This is an example of a problem that is complex, and the best way to solve it is methodically. Break it into pieces. Do things in order. What do we need to know first? If we're going to react something with something, you've got to have a balanced equation. That's the only way to map out the next steps. Then you put what you know into that scenario. So that's why we wrote here and here. Then you have to decide limiting. Which one's limiting, which one's excess? If there is, in fact, excess chloride, then you find out how much is consumed, then by difference, how much is left over, and it's all downhill from there. If we had determined that the chloride source is limiting, it's all used up, then the answer would have been 0, right? No chloride left over. All right, 1120. We're still on difficulty 3. Solution stoichiometry. Let's see, how about this one? If this one's worth tackling. Let's see if we can find something else. This one's kind of complex, I'll admit. So maybe it's worth working. Let's do that. All right. Okay, so let's read through the problem, find out what the question is, then go back and extract information from it. This is just a preface statement here. it doesn't mean that you don't need to know it, because they give you the reaction that you need. Hydrogen peroxide plus sulfur dioxide yields sulfuric acid. Okay? And when this sample of coal is burned, it produces sulfur dioxide. We're going to find out how much sulfur dioxide was produced because we can titrate the acid, sulfuric acid, with a known concentration of sodium hydroxide and find out how much that is, right? So we've actually got two coupled reactions, right? We've got the first one, H2O2 plus sulfur dioxide yields sulfuric acid. And then we've got the acid-base titration, which is sulfuric acid plus sodium hydroxide yields sodium sulfate plus water. Okay. Okay. So the sulfuric acid is titrated with standard sodium hydroxide. Here. We also know that the sample of coal was 1.178 grams. 1.178 grams is the total mass of the coal. We'll keep that. We'll need it later at the end. What we need to find out is, what is the percentage of sulfur in that sample? Actually, you've got three reactions. How did we get that sulfur in the first place? Well, we have the coal, which has sulfur in it, plus oxygen yields sulfur dioxide. So when we find out how much sulfur dioxide, we've got to convert that to how much sulfur that represents. All right, so we're working backwards from here to there. What are we given? 28.44 milliliters of 0.1 molar sodium hydroxide. 28.44 milliliters of 0.1 molar sodium hydroxide exactly titrates sulfuric acid. Okay, so how many moles of this would exactly match moles of that? Well, this is so many millimoles, 2.844 millimoles, right? That times that, 2.88 millimoles. So how many millimoles of sulfuric acid does that represent? Well, this is sodium hydroxide. This is sulfuric acid. What's the ratio? 2 to 1. So half of that. .422. 1.422 millimoles of sulfuric acid. Okay, so where did that come from? It came from right here, 1.422 millimoles. All right, how many millimoles of sulfur dioxide is that? All right, is that balanced? One sulfur, 2, 4 oxygens, 2 hydrogens. Yeah, 1.422 millimoles of sulfur dioxide. All right. How many millimoles of sulfur is that? It's 1.422 millimoles of sulfur, right? Because there's one sulfur for every one sulfur dioxide. Right? So this is easier than I thought it would be. Okay, how many moles is that? Because we're going to have to convert it to mass, right? So we have 1.422 times 10 to the minus third moles of sulfur. Right? There's your milli, and there's your milli right there. So moles per gram. So what's the molar mass of sulfur? 32.07. There we go. So how many grams is that? Right? Get the calculator out. 32.07. So I get 4.56 times 10 to the minus 2. Grams of sulfur. What's the percent? It's sulfur divided by the total times 100. So we need divided by the total 1.178 times 100. .87%. Okay, I don't know if that's high. It's probably high sulfur coal, not low sulfur. So let's see if the system likes that answer. 3.87. Yes, it did. Okay. I know that took a lot of work. But the key, I think, is recognizing how the reactions are coupled. What's your end game? The end game is percentage, right? Sulfur divided by the total. So you need the sulfur. Well, you can't tell the grams yet until you find out how many moles. So you have to say, all right, you can, this information is given, so you can determine that. Then how is that related to the titration? Well, the titration is the compound that came from this reaction, right? So those are equal. And then the stoichiometry here says those are equal. And the composition says those are equal. Then you convert. So it's really not that difficult. It just looks hard. That's why they give it level 3, because it looks hard, but it's really not. If you break it into pieces, logical pieces. Okay, 11:30, got 20 minutes. Let's see if we can find, I don't want to do a 5, maybe a 4, if they got a 4. Let me see, let me go up here. There's a 4. What volume of 0.184 sodium iodide we're going to neutralize? No, that's not a 4. That's too easy. Let's get a hard one. Calculate the mass of silver chloride formed and the concentration of silver ions remaining in solution. Yeah, it could be worthwhile. Let's see if there's another one that could be useful. Nah. Yeah, it was too easy too. Let's look at that number 5. I wonder if that one's particularly difficult. Where did it go? Getting warm. Here it is. A solution of citric acid contains 182 grams per liter of solution. Calculate the normality of this solution. That's really not a 5. I wonder if there are any other 5s up here. Nope, that's the only 5. Okay, so we'll do this one. All right, let's see. I didn't walk too far, did I? Okay. So we've got a solution of citric acid, H3C6H5O7. See, is that, yeah, be sure got it all up there. And this solution contains 182 grams per liter. 182 grams per liter. Okay, that's a given. Calculate the normality of the solution. That should be fairly simple, shouldn't it? We want to know the normality. Well, we need to know the molarity first, don't we? 182 grams per liter. We need to know moles. So we need to know the molar mass of that compound. I got a lab that my students do in general chemistry. They actually calculate by titration the molar mass of citric acid. It's pretty fun. See how close you can get to the true value. Okay, so we need, oh, I don't need the chart for that. How many hydrogens do you have? Notice that there are 3 of them here and there are 5 of them there. That could be the tricky part. These 5 do not dissociate from the molecule. That is, they're not acidic. Only these 3, right? And that's the way we write acids. We would write it something like this, H3A. Everything else over here is intact. These 3 hydrogens dissociate when you put them in solution. That's important to know for normality. That's the difficulty level. It's only those 3, like phosphoric acid has 3 hydrogens. Only those 3. Okay, so we need molar mass of citric acid. So we have 8 hydrogens, 8.08, right? 8 times 1.01. Carbon, 6 times 12.01. Added together, and then 7 times 16 for oxygen. 192.14. Right? That leaves us with moles per liter. Molarity. All right, so let's see what that is. It's going to be less than 1, right? 192 into 182. 182. 0.947. 0.947 molar. And how do we determine a normality from molarity? How many hydrogens are in there? 3. So 3 times this gives us normality. 2.84. Let's see. 3 significant figures. 2.84. All right, let's see if that value satisfies. It certainly does. All right, so that's the only level 5 that I could find. Yep. What's this level 4 at the very bottom? I think we looked at that one before. Okay, I think that's sufficient. What we'll do, this is Thursday, what we'll do Tuesday is I'll go to this document right here, the review document, and we'll work through those problems. So between now and then, you should work all the homework problems, right? And get into the review document so we can find out if there are any types of problems that are specifically troublesome for you, and we can iron those things out so that you can ace the exam. How about that? Okay. Well, I've talked enough for one day, I think.